In this video, we're going to look at maximizing utility, and instead of using the cobb-douglas utility functions that I've been using in most of my videos, we're going to look at a different kind of functional form in this video. And in particular, we're going to look at a utility function that is of the type that we call a quasi-linear utility function. Now, a quasi-linear utility function typically has this kind of format where your utility equals some function of one of the variables. For example, let's just say in general, some function of x that is not linear plus y. And this could be 2y or 3y or 1/2 y, for example. But typically this f of x will be a concave function. The simplest example, and that's what we're going to look at right now, is what if we had your utility is equal to the square root of x to the 0.5, plus y. This would be a very simple kind of quasi-linear utility function. Now, why do we call it quasi-linear? Well, because when you graph straight lines, you can graph them as being parallel to each other, and basically that's, if you look down here at this graph of this utility function, what's going on is that these indifference curves here are parallel to each other. To be a little bit more clear about that, the slope, if we look at, say, x equals 2 here, and we go straight up in the y direction, that the slope of this blue indifference curve at this point, x equals 2, is the same as the slope of this gray one here, and that's the same as the slope of the purple one at this point, x equals 2. So as y increases, but we're holding x constant, the slope is identical, and so these are kind of parallel in that y direction here. So with a quasi-linear utility function, one of the big differences between this kind of utility function and a cobb-douglas is that with a cobb-douglas utility function, let me bring one of those up here just for a minute. So you can see here in this cobb-douglas, which usually has a functional form of this kind of type here, utility equals x raised to some exponent times y raised to some exponent. With a cobb-douglas, these indifference curves never intersect the x or the y axis. They just indefinitely get closer and closer to the y and the x axis, but they never actually touch. So with a cobb-douglas utility function, there's never going to be a solution where you buy all y and no x, or all x and no y, for example. Even if, say, the price of x is $1 million, you're still going to buy a tiny bit of x, because these indifference curves never touch the x or y axis. Now, with the quasi-linear utility functions, they do intersect the y-axis and the x-axis. So if you look at this gray one here, this is the indifference curve for two utils. It intersects the y-axis here at y equals 2, because you can see here that if y equals 2, the utility will equal, and x equals 0, utility will equal 0 plus 2. So that gives you 2 utils. But since this is additive, plus instead of times, then you can see that it also intersects the y-axis down here at 4. No, sorry, x-axis at 4. Because if we have 0 y but 4 x's, that also gives us 2 utils, because utility equals the square root of 4 plus 2. So these are very different kinds of animals from a cobb-douglas utility function. One thing you have to watch out for, because these indifference curves do intersect the x and y axis, is you have to watch out for these cases where you buy no x or no y. So there are going to be cases where you want to maximize your utility at a corner point, a corner solution. So when we say there's a corner solution, that means that your budget line has a slope such that suppose a budget line looked like this. It was very, very steep. Well, in that case, you're going to get your maximum utility. Well, sorry, it's our maximum utility. That's the wrong one. Let me erase that. Suppose instead your indifference curve was very flat. Maybe that'll be a better way to visualize this to begin with. If your budget line was very, very flat, where you hit your maximum utility here is going to be at a corner, and a corner solution means that we're only going to buy X in this case and no Y. Now, on the other hand, we could have a very steep indifference curve here. Suppose our indifference curve looked like this. Very, 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 very steep. The highest indifference curve we could hit in this case would be the purple one. And again, that's going to be a corner solution, where our solution is going to be, in this case, we might buy 2.5 Y's, but no X's. Why is this something that's so important to watch out for? Well, if you look at this purple indifference curve, it actually doesn't stop there. The purple indifference curve actually is going to keep going back here, where at negative, we're actually having negative values of X here, which aren't really possible. You can't go out and buy a -1 hamburger. The problem comes with the mathematics. Remember our two equations we try to solve here. Let's go ahead and set those equations up. What we normally do is we look for a case where the slope of the budget line equals the slope of the indifference curve. That's going to be true for an interior solution. An interior solution means that we're in the interior of the graph where we're buying some X and some Y. That's always going to be the case for those cobb-douglas utility functions. Here for a quasi-linear, we need to watch out for cases where we actually are not going to have that condition met. The slope of this budget line, the yellow, is actually going to be much steeper than the slope of this indifference curve. It's going to kind of cut through it here whenever we have one of these corner solutions. So let's work a couple of these problems, and we'll see how we can keep our eye out for cases where we're going to have those corner solutions. Now, just like always, what we're going to want to do is set up two equations and two unknowns. And our two equations, when we maximize utility, are always looking at where the marginal rate of substitution, the slope of the indifference curve, equals the ratio of the prices. So marginal rate of substitution of X for Y. And keep in mind, where did we get that marginal rate of substitution from? Well, the marginal rate of substitution of X for Y is the ratio of the marginal utility of X over the marginal utility of Y. Let's go ahead and find that first. Now remember, how we find the marginal utility with respect to X is to take the partial derivative of the utility function with respect to X. And the marginal utility of Y will similarly be partial derivative of this function with respect to Y. So taking the derivative of this function with respect to X is just finding the derivative of the square root of X. Now the square root of X, keep in mind, is the same as X to the 0.5, so to take the derivative of that is equal to 0.5 times X multiplied by the exponent, and then subtract 1 from the exponent. So 0.5 minus 1 is to the minus 0.5 here. So 0.5x to the minus 0.5, which we can rewrite as 0.5 over x to the 0.5. Now, taking the marginal utility of y is just the derivative of this function with respect to y, which is derivative of y is just 1, just the number 1. So the marginal rate of substitution of x for y here, function, is just going to be 0.5 over x to the 0.5 or over the square root of x, either way you want to write that, divided by 1, marginal utility of y. So well, that doesn't change our function at all. So that's our marginal rate of substitution function. And so our first equation here is going to be marginal rate of substitution equals the ratio of the prices. Well, I haven't given us a setup yet for looking at prices, so let's assume very simply here that in this situation, let's suppose the price of x equals 2, the price of y equals 1, and let's assume again that we have a budget of 4. Okay, so then this first equation here is going to be marginal rate of substitution, which equals 0.5 over x to the 0.5 equals the price of x over the price of y. 2 over 1, which just equals 2. Our second equation is the budget line here. So our budget line equation number 2, 2x plus 1y equals 4. So price of x times how many units of x plus price of y times how many units of y, 1y, equals the budget, 4. So solving these two equations with two unknowns, let's see what we get here. So let's normally what we've done before is solve this equation for y and plug into the budget equation here. That's not going to work in this case. We're going to have to solve this for x. So let's solve this equation for x and plug that into the budget line over there. Let me erase that little mark. Okay, so we're going to have 2x to the 0.5 equals 0.5. Let's divide both sides by 2 here, and we're going to end up with x to the 0.5, or the square root of x, equals 0.25. And so now let's square both sides, and we'll be able to solve this pretty easily. X equals 0.25 squared. So in this case, the amount of x we're going to buy is going to be a very small amount, only 0.0625 squared there. Now let's draw this over in our indifference curve map over here and make sure that this looks like it makes sense. So if we have this budget line right here, then with these prices, if we have $4 and the price of y is 1, then we could afford 4 y's. And since the price of x is 2, we could afford as much as 2 x's. And now if we connect those two dots and we look at our budget line, let's see where it looks like that might be having the same slope as an indifference curve. And sure enough, I would agree that it might have the same slope right there, and that is not going to be very much x at all. Now let's solve to see how much y will buy. Now it's kind of interesting here that since there's only x in this equation, that it doesn't really, we don't have to solve two equations for two unknowns. We can just solve this for x directly. Just plug that into the budget line to see how much y we will be buying then. So 2 times 0.0625 plus y equals 4. And so that's going to be equal to 0.125 plus y equals 4. Subtract 0.125 from both sides, and we're going to get y equals 3.875, I believe. Doing that in my head. I hope I did that right. And if we go back over here and we look at our orange point, then yes, I believe that could be 3.75, where we were just guessing based on the graph where those two things are going to be having the same slope. All right, nothing real complicated here. We've done that before. Let's change the prices a little bit though, and let's see what happens. Let's increase the price of x from 2 to 4 and see what happens. I think that will give us a corner solution in this case. So let me erase all this so we can have a better working area here. And let's see what changes when we change those prices. So let's change the price of x to 4. And let's see what changes. Okay, so let's set up our equations. The marginal rate of substitution, 0.5 over x to the 0.5 here. So 0.5 over the square root of x equals the ratio of the prices. Price of x over the price of y. So let's see here, it's going to be 4 over 1. And so now if we solve these equations here for x, this equation for x, oh sorry, we're also going to have to change that budget line, 4x plus y equals 4. Now our budget line is going to look like this, because we can only afford one x if we spend all our money on x. Let's see what happens in this case. Now looking at the math, I don't think we're going to get a corner solution here. But let's see what happens. Solve this for x. Well, we're going to get 4x to the 0.5 equals 0.5. Divide both sides by 4, and we're going to get x to the 0.5 equals 0.5 over 4, or 0.125, and then square both sides here, and we're still going to end up with consuming a positive amount of x. If we're going to hunt for one of these corner solutions, we're probably going to have to do it on the other end of these indifference curves here. So our optimal amount of x in that case is going to be 0.015625. So it's looking to me like a corner solution on this y-axis here is not going to be possible, because what's happening is this function is getting steeper and steeper and steeper and steeper as it gets closer to the y-axis here. So that's not going to be possible. So let's go the other extreme and see if we can find a corner solution down here. Okay, so if we go the opposite extreme, then let's raise the price of y to be 10 and the price of x to be 1. Now if we draw this budget line with a budget of 4, you could only buy 4/10 of a y with your money if you spent it. It's just the budget divided by the price of y. So our y-intercept is going to be way down here. Now our x-intercept, we could buy 4 x's, since x's are very cheap here. Okay, so let's put that point there, and if we connect these two dots, we'll see what our budget line is going to look like there. And then we can solve this equation to see what it tells us. So again, our two equations, marginal rate of substitution, 0.5 over x to the 0.5, I'll write that as square root of x this time, same thing, equals the ratio of the prices, x over y, so that's going to be 1 over 10 now. Our second equation is going to be the budget line equation. The price of x times x, 1x, plus 10y, price of y times the number of y's equals 4. So here's our two equations. Now let's solve these two equations and see what pops out here. Solving this for x, we get 1/10 times the square root of x equals 0.5. Multiply both sides by 10, and you get the square root of x equals 5. square both sides, x equals 25. You should already be noticing a problem here. The optimal x is 25 units of x. Well, we can't afford 25 units of x with our budget. See, we can only afford 4. Now again, what this is telling us is that this indifference curve, if we kept graphing it out, it's gonna kind of go down like that. At this point, the indifference curve is actually steeper than the budget line. So we're not really finding that it's going to be tangent at this corner point, although that is going to be our best utility that we can get. What this is telling us, whenever you have a solution that tells you you want to buy more x than you can actually afford, what it's telling you is that you want to spend all your money on x. Now, another way to see this is if we plug x equals 25 here into this budget line equation to see how much y we would want to buy, then 25 plus 10y equals 4. Subtract the 25 from both sides and we get 10y equals negative 21. So the optimal amount of y is negative 21 over 10, or minus 2.1. When you get a negative solution for one of the values, first double check your math to make sure you haven't misplaced a negative sign. But generally what that's telling you is if you want to buy a negative amount of a good, then the amount of the other good you're supposed to buy is more than you can actually afford. What that's telling you is that you actually have a corner solution. Spend all your money on x, and that is the best that you can do in this situation.